We're now going to apply the Hückel method to a linear polyene, and I've drawn a cartoon of a linear polyene up here in the upper right hand side. So it's going to be a string of carbon atoms that all lie in a plane. Remember, that's a feature of conjugated pi systems, and polyenes are in effect conjugated pi systems. And in these carbon atoms, they all have a p orbital that is sticking up perpendicular to the plane. So we're looking edge on. All of the carbon atoms lie in the plane. We're looking at from the edge, and all of these p orbitals stick perpendicularly out of that plane. Now, I want to number these carbons just to keep this clear and how we're referring to these. I'm going to start at the left end starting with 1 and go all the way up to n. So our basis set in this particular treatment is essentially going to be the 2p orbitals related to each of these carbons. I'll call 2p1, 2p2, 2p3, and so forth, all the way up to 2pn. And I won't specify what n is. However, I'll note that typically we do this treatment for n as an even number, so that there is a full number of double bonds that are present here. All right. Now, according to Hückel theory, the overlap integrals are going to be 0 when I and j are not equal to each other, and 1 when they are equal to each other. So this is just the delta ij. And our hij's are going to have two different possibilities. When I is equal to j, then I'll have hij is equal to alpha. When I is equal to j plus or minus 1, then it's equal to beta. Otherwise, it'll be 0. All right, so what does this mean for setting up the secular determinant? Well, we need to look at the connectivity. So as I've drawn this here, if I look at the connectivity of the carbons, I have 1 that is connected to 2, 2 is connected to 3 and to 1, 3 is connected to 2 and to 4, and so forth. And this will continue going. So this means that I will have elements that are non-zero that correspond to H12, H23, H32, and so forth. All right, so I can directly read off of this which of the elements of my secular determinant are going to be non-zero. All right, so let's draw this out. Let's draw what the secular determinant would look like. Well, H11 is I equals j, so it's up here. H11 is alpha. S11 is just going to be 1, so alpha minus E times 1. All right, right below it is H21. Since H is since 2 is plus or is within 1 of 1, that means this one will end up being beta. Likewise, H12 will be beta. H22 will equal alpha minus E times 1. All right, remember each of these diagonal elements is hij minus E times sij. So when I don't show any s there, that's s is equal to 1. When I don't show any e, that means s was equal to 0. Well, this pattern is going to continue for a linear polyene throughout the secular determinant, and we'll come down here to the lowest one being alpha minus e. It will have betas on above and to the left of it. All of the other elements in this secular determinant, I should say, one off the diagonals will all be betas. But all other elements in this secular determinant will be zeros. All right, so basically what we have is a banded determinant. We have non-zero elements on the diagonal, and we have non-zero elements that are one off the diagonal. Right, and all of this would be equal to 0. Now, we can certainly solve this directly as it's written here, and that would be fine. But we can simplify this also. For example, if we factor beta out of each and every element in this matrix, it turns out that the rule of determinants would say that if this has got n different elements, if there are n total rows here, then I would have beta to the n to factor it out. And then at each of the diagonals, I would have alpha minus e over beta, because I've factored the beta out. For the one below that, it would just be 1. And then I would have zeros the rest of the way down. For the middle one here, I'll have alpha minus e over beta, and 1 again, and so forth. So the whole secular determinant has diagonal elements that are alpha minus e times beta, and all of the other elements are as written here. Where there used to be betas, now it will be equal to 1, sorry. And up in the upper and lower triangles, I'll have zeros. So this is what my secular determinant becomes. But I can simplify this once again by simply setting x equal to alpha minus e over beta. Now, what this means is that when I solve what this gives me for x, I'm going to have to then convert it to e by undoing this relationship. So in other words, e would be equal to alpha plus beta times x. I'm sure, sorry, that should be a minus. Alpha minus beta times x. Okay, so if I make that simplification, now my secular determinant is going to have the following form, and it's actually a very simple form. All of the diagonal elements will be x. All of the elements 1 off of the diagonal will be 1. And everything else in this determinant would be zeros. And you notice I've left off the b in front of here. Well, this whole thing is equal to 0, so I can just divide both sides by beta to the n and get rid of it. So these values of x that I get now from solving this determinant equal to 0, I can convert to energies here and get the final result. Now, when we do this, for the n atom linear polyene, this is actually a result that we can calculate exactly. I won't do it here because I don't know that it serves any purpose to go through the mathematical derivation. But basically, what we would learn is the following. The nth value of x, because this will be a polynomial of order n, order capital N, one of the solutions of this could be written as minus 2 cosine n pi over capital N plus 1. All right, and let's not worry too much about where that comes from, but remember that this is equal to alpha minus E sub n over beta. So when I solve for E sub n, what will I get? Well, the values of the energy levels for this linear polyene would be given by the following expression under Hückel theory. All right, so it's actually a very neat and tidy expression here for these energy levels. I will say that we can also get expressions for the coefficients of the eigenvectors or the eigenfunctions. And in effect, what happens is if I write my molecular orbital for the nth molecular orbital, that would be equal to a summation, as we've written it above. Now let me make these k's. Summing over k. And I can solve for these coefficients by solving this eigenvalue problem. This is basically an matrix eigenvalue problem. And when I get those coefficients, it ends up being something like this. It'll be square root of 2 over n plus 1 times the sum over all of the atomic orbitals, so k from 1 to n. And the coefficients are given by sine of n k pi divided by n plus 1. And so these are the These are the things that are going to multiply by each of these 2p functions. All right, I get it that this is a complicated looking expression, but we're going to see pictorially what this really means in just a moment. I'll simply point out, though, that you can calculate these things. I mean, you just plug numbers in. So these n and k are both integers. N is the particular molecular orbital that you're interested in. K is just going to sum always from 1 to capital N. So it's just a sum over the atomic orbitals. And you know how many atomic orbitals you have in your basis. So all you're doing is weighting these different p orbitals. These things here are the basis functions. So this one would be 6c phi of 2p for the number 6. So that's all you're adding up here. So let's see what those look like. Okay, what I want to do is draw a picture, if you will, of how we might put these together to construct the molecular orbitals for a linear polyene. Okay, so to do this, let me simplify this by, we're going to do this for n equals 4. So let me put that over here. N equals 4. So what we're talking about is butadiene. Okay, that way I don't have to be so abstract about all of this. So I'm going to draw my molecular orbitals down here. And actually what I'm going to draw first are the atomic orbitals that add up to make these molecular orbitals. Now remember that the coefficients here were given by sine of nk pi over capital N plus 1. Capital N in this case is equal to 4, so this is actually multiples of pi over 5. All right, so when I do this, here's what I would get. Okay, for the very first orbital, so this is for psi 1, or phi 1, I guess I should say, phi sub 1, so the first molecular orbital. I'll have a smaller contribution from the first orbital, a larger one from the second, a similar one from the third, and a small one again from the fourth. And all of these are an additive combination, so they're all going to be in phase with one another. So there'll be something like that. For the second one, well, it turns out that 2 of my coefficients here will turn out to be negative. So what they do is they turn the pi orbital upside down. So the first 2 will be oriented in the same way with the positive end on top, but the next 2 will be oriented with the positive end on the bottom. So we'll end up like this. And to draw in the negative parts of these lobes. So we'll have a molecular orbital that looks something like this. All right, now when we get to the third one, now we'll actually have an orbital that is larger on the outside and then smaller on the inside and larger on the outside again. You'll notice that there's a bilateral symmetry to the size of these orbitals. Maybe it's not so obvious from the way I'm drawing them, but there is. And what we would find in this case is that we have a positive coefficient for the first orbital, negative coefficients for the next 2, and a positive coefficient for the fourth orbital. And so, well, let me finish my coloring of the orbitals. Okay, and finally for the fourth one, we'll have orbitals where the p orbitals are roughly the same size, but they're going to alternate sign between every pair of them. So we'll have positive, negative, like that. Okay, well, very interesting. Now, if I were to now combine these, so remember this is a sum over all of these atomic orbitals to produce the molecular orbitals that they represent. So now I'm going to sum them up, or at least the best I can pictorially. All right, for this first one, I've got all positive lobes above the line and all negative lobes below the line. So this is going to end up being a big cloud of electrons up here and a big one down here looks a lot like a pi orbital. Okay, it's a pi orbital, but it's extended over the entire molecule, over all 4 atoms. Okay, I guess you could also say it looks like a p orbital. Okay, for the next one, what do I have? Well, interestingly, I have a node right here in the middle. And in fact, if I look through these orbitals, I have a node here and a node here. And I have nodes here, here, and here for the top one. Okay, but for this second one, what is it going to look like? Well, I'll have a pair of orbitals, whoops, like this, and a pair of orbitals that are combined like this. So I still have my node here in the middle, but now I have positive lobe up here, positive lobe down here, and here I have negative lobe here, negative lobe here for that next p orbital, for the next pi molecular orbital. Okay, for the third one, and actually I need to move my line up a little bit here to give me a little bit more space. What will I have? Well, I'll have a big orbital out here. I'll have a pair of orbitals down here and a big orbital out here with the positive lobes here, here, and here, and the negative lobes here, here, and here. And then finally, the fourth one is going to pretty much look like this, so I'm not even going to redraw it, but it will look something like that. But you can see that these molecular orbitals now preserve that nodal structure that we observed between the p orbitals. And again, our nodes go from 0, 1, 2, and 3. So the number of nodes increases as we go higher and higher in energy. Now, what's not so obvious from this picture, but I'm going to try and draw the analogy for you here, is I want you to remember the particle in a box eigenstates. Now, I know it's been a long time since we looked at particle in a box, but the lowest eigenstate down here was one that had no nodes. So if we just drew a straight line across here, that's what it looked like. Well, this is like that lowest particle in a box eigenstate. If I go to the second particle in a box eigenstate, it looks something like this, with one node in the middle. Okay, well, that's what I've got here, is the second particle in a box eigenstate. The third one looks something like that. Well, that's what I have here, is this third particle in a box eigenstate. And the fourth one, similarly, something like that. So you can see there's a parallel structure here between what we're getting out of the Hückel theory for these pi molecular orbitals and the states that we found in the particle in a box. And in fact, these would be a reasonable facsimile of a cross-section of these molecular orbitals. If we were to slice these orbitals in half and draw the cross-section of that, they might look something like these orbitals that we've drawn here from the particle in a box. Now, I will finally mention that if we were to apply the Pauli principle to this, we would find that, in fact, there are 2 electrons possible in each of these pi molecular orbitals. So what does that mean? In what the Hückel theory is predicting is that we will fill this orbital and we will fill this orbital because we have a total of 4 pi electrons in butadiene. It's got 4 atoms. There's 1 electron in each carbon. That is 1 p electron. So that means we have a total of 4 p electrons, a total of 4 electrons in the pi molecular orbital system. So we're going to fill these 2. Does that mean we have an antibonding orbital? No, what this is telling us is that I have 1 bond over here, 1 pi bond over here, and 1 pi bond over here. So I have basically, I have this kind of situation for butadiene. 2 pi bonds separated by a sigma bond. There's no pi bond in the middle because that's where there's a node in the pi molecular orbital.